We've spent a decent amount of time looking for limits numerically by using tables in computational software, graphical software like Desmos or a graphing calculator. Well, now we're actually going to go ahead and use the graphs themselves. So we're going to make some very important distinctions here in a moment. Let's begin with part A. We don't even know what the function is. So we don't actually have the math this time. We just have the graph. And you'll notice that there are open holes there. We call these singularities. And in particular, it's been moved. So imagine if you're traveling on the freeway and you're expecting to get to Lancaster. When you get there, there's an empty hole. And Lancaster has been moved to Ventura County. Okay, so it's not where it's supposed to be. All right. So for part A, we're looking what happens as we approach 4. So we're traveling on this road, and we travel on these roads. We don't start traveling from, let's say, San Diego or from Nevada. Okay, we actually start traveling close enough to home. Like we're leaving Los Angeles, coming to Lancaster. So we're traveling on this road right here. We're trying to approach this point. Now we're approaching an x value of 4. So when I'm approaching, that means I'm going to the right. I'm trying to get to this 4 right here on the x-axis. But as I do that, in this particular case, my graph is moving further up the y-axis. And as I'm going to this point right here, I'm supposed to be getting close to a positive 7. And if we look at this from the other direction, if I use this graph and if I'm approaching it from the right means I'm going this way. So from the right, it's kind of doing this thing and then coming back down, and it's approaching 7 as well. So as far as we're concerned, from the left it's approaching 7, from the right it's approaching 7 as we're trying to get closer to 4, and so the limit is 7. However, notice the distinction now with the notation. This is not a limit right now. This is asking for the actual value of the function. So in other words, if I were to ask for an x value of 4, what would the y value be? Well, at x equals 4, y is equal to 2. So we note that the limit isn't what happens at when we get to that point. Because when we get to this point, as far as we're concerned, it looks undefined, but it's actually not undefined because it's been moved somewhere else. So in this case, part A, the limit was 7. Part B, it wasn't undefined. So if we were to put this in a calculator, it would have told us that at x equals 4, y is equal to 2. So this is defined. This function is defined for x equals to 4. But the limit was 7, approaching the left and the right. Okay. What about as we approach negative 2? Well, from the left, as we're going closer to negative 2, I'm getting closer to this value of 5 over here. And the same thing as I'm coming from the right, I'm getting closer and closer to 5. So, we're driving on this freeway, we're expecting to get to this city. All right? But the problem is when we actually get to the city. So this is the function. This means we got to the city. We are in the city. Well, this city is not where it's supposed to be. So it's like as soon as you go ahead and actually hit the city limits, you've been transported magically to somewhere else. And this somewhere else in this case is going to be positive 3. So just be aware that the limit is what we expect to be there when we get there. And the function is telling us what is actually there, if it's there. So in this case, again, it's defined. You saw previously what happens when things are undefined. Undefined would mean that there are no closed dots anywhere or a closed portion of the graph anywhere along this value. For example, at 4, right? At 4, there would be nothing that's actually dark. Okay? But since there is, then we have it to be defined. If, for example, this graph had nothing here at all, okay, then that's when we get the situations as we did with previous problems where we said, okay, at f of 4, it was undefined because there was just an open circle and nothing ever filled it in anywhere ever. So for every problem up to this point, we've always had you look from the left and from the right. We were driving to the same location from two different positions. Well, let's introduce you now to a one-sided limit. So by us actually stating that there's something called a one-sided limit, that implies that there are two-sided limits. So technically speaking, every limit we've looked at so far was a two-sided limit. So whenever we use the word limit in its proper form, it actually implies that it's a two-sided limit. Well, we're going to look at one-sided limits right now, meaning that it is focusing on only one side. So if you notice this first limit, it has a little negative sign on top. That has no mathematical bearing on how you do the problem. This is simply stating that you're going to be traveling from the left. And that's it. That's all that matters. Whereas with this one, with a little positive on top, it looks like an exponent, by the way. Okay, there's no mathematical value except that it's letting us know that we're looking at the limit only from the right. Okay, and one-sided limits are only limits. So that means we only look at it from the left if it's a little negative exponent, or only from the right if it has a little positive exponent. For this summary, can a function be undefined and have a limit? Explain. And can a function be defined and have a different limit than what the function is defined at that point? Explain. Welcome to pre-calculus. Now I know some of you are thinking, Mr. Over, this is calculus stuff. Yes and no. You're going to find multiple pre-calculus books that cover limits as their last chapter. And you're going to find every calculus book talks about limits as well. However, the treatment that limits are given in calculus is so limited. It's not limited in the scope, in the depth, but in how much time they spend in developing the idea. It's kind of a 1 week thing that they do. So everything we've been doing and will do in the next few weeks for a total about of a month and a half will be covered in your calculus class within 1 week. And so I felt that it would be appropriate to give you a greater depth and understanding so that you have a better chance in future courses. So here we have in problem 5 what's something called a piecewise function. And you'll notice that this function is defined by these two expressions right here. And these are conditional. So if x is less than 1, the graph will do this. If x is greater than or equal to 1, it'll perform like this. So if it's less than 1, it'll be a parabola. If it's greater than 1 or equal to 1, it'll be a line. Every piecewise function is different. There are some special piecewise functions that we might look at later. But for now, what you need to understand is, let's look at this graph. How it's acting a certain way, and then all of a sudden it acts a different way. And you'll notice that because this is a greater than or equal to, it actually has a solid dot right here. This is a less than, so there was an open dot at that point. Okay, so let's look at our thingies. A, this is the limit as x approaches 1 from the left. That's how we read this, from the left, 1 from the left. It's not a negative 1, it's 1 from the left. And that's all that matters because A is a one-sided limit. So from the left, I mean, it's traveling, and then it's going to here. All right, 1 from the left. So 1 from the left is approaching a y value of 2. It doesn't hit it. It's just approaching it. What is the limit as x approaches 1 from the right? Notice this little positive sign right there. That's from the right. So from the right means I'm coming down this road. And from the right, it's approaching a y value of 4. Now, these parts A and B, they do have answers because these are one-sided limits. However, let's ask the deeper, darker question, which we've been asking multiple times up to this point. What is a limit as x approaches 1? Well, we've looked at numerical calculations in tables, and we've looked at some of the graphs already. The limit exists if it's the same if it's approaching the same number from the left and from the right. But let's be real. From the left, it's approaching 2. From the right, it's approaching 4. They're not approaching the same number. So because they're not approaching the same number, we say that the limit does not exist. Okay. Now this is only is a case like we're showing here for a two-sided limit. Notice that for one-sided limits, we actually had answers, we had numbers that we were approaching. But in the case of a two-sided limit, if it can't agree, then it doesn't exist. There's no deal. Now, just for kicks, what is f of 1 for this function? Well, if we plug in a value of 1 and we look all the way up and down, we do know that it's filled in at this point. So f of 1 for this problem is 4. So be aware, these are functions, function notations from Algebra 1, Algebra 2. Now we're doing the limits. And the one-sided limits, they existed and they were converging towards a particular number. But part C, they weren't agreeing on what number to approach. And so that was D and E, which stands for does not exist. Problem 6. Let's chat about these things. Limits indicate that a graph can get really close to values without actually reaching them. Yes, that makes sense. We've seen that, right? We saw that with the tables. We saw that with the graph. Whether the whole is empty or has been moved, if that point has been moved somewhere else, that doesn't matter. The fact that we're traveling on the road and we're getting really, really close to a certain location that should be there, that's what the limit is about. So this one, part A, that does make sense. Part B, I'm working with a function that is undefined at 5. So the limit as x approaches 5 does not exist. Well, that depends, right? We could draw a couple of examples of that. So we could, for example, draw a graph where we have, here's our function, right? It's undefined at 5, which means there's a hole, and I can't find it anywhere else in that 5. And if we're getting closer and closer to that from the left, it's approaching 5. From the right, it's approaching 5. So this is undefined, and the limit does exist. Okay, so that's one example where what we're saying here is not true, because it does exist. However, we could have a weird function like this, right, which is undefined at 5, and approaching from the left, I'm getting to this point right here, but approaching from the right, I'm coming to this point down here. And they're not going to be hitting the same number. Right here, I'm hitting a positive number. Here, I'm hitting a negative number. So in this case, it's a D and E. So just be mentally aware and think, okay, well, could it be possible or could it not be possible? So part B, yeah, it could make sense, but it also could not make sense. We could find multiple counterexamples for that. Part C, I'm working with a function for which the limit from the left is not the same as the limit from the right. This means is not equal or is not the same. So from the left and from the right, they're different. So I cannot draw the graph of a function near A without lifting my pencil off the paper. Oh, you should try this out. This is pretty enjoyable. So check this out. So we know, for example, that like the one I just drew, right? Like I have this one here, and notice I'm not gonna pick up my pencil. Okay, I'm gonna just go ahead and go floop, and then floop. And what happens is this is undefined at this point, but if I'm going from the left and I'm going from the right, it's approaching the same number. So what I just drew without lifting my pencil actually is a pretty, I'm just going to be sacrilegious for people listening out there, but it's kind of a continuous, right? We have a singularity, we have a whole, but it's kind of predictable what's happening. Okay, so it's getting to the same point. Now, could we draw something like this without lifting our fingers off or lifting our pencil off the paper? No. Right, and that's what problem C is talking about. It's saying, hey, the limit from the left is not the same as the limit from the right. Okay, And if that's the case, I have to pick up my pencil, because if I didn't pick up my pencil, I could draw it over here, or I could draw it, um, I could wrap around and go over here or whatever. That's not a function anymore anyway. I could draw it like right here. It's connected, and so from the left and from the right, I'm still going to be approaching the same thing. So can I, if they are different from the left and from the right, I cannot draw the graph of a function without lifting my pencil. That makes sense. That is very true.